Good morning, all of you. In the last class, we have discussed what is receiver diversity. We have studied two kinds of diversity combining techniques called as selection combining and maximal ratio combining. Today's class is going to be very interesting because we are going to see transmit diversity or the transmitter side diversity. I'll give you a simple analogous example. I am speaking to you. Okay. I am a single transmitter and you are multiple receivers. Each student will receive different amounts of information whatever I am telling you. That is the reason why each one of you are scoring different marks. Am I right? So this is one of the ways in which you can analogously come into a understanding about how a single input and multiple output system works. Receiver diversity. Now we are coming into the next part where we have multiple transmitters, okay, and for our simplicity we will consider we have only one receiver. In MIMO systems we have both multiple transmitters and multiple receivers, okay. So today we will be considering a condition where we will be having multiple receivers. So in transmit diversity, there are multiple transmit antennas and the transmit power is divided among these antennas. So transmitter diversity uses multiple transmit antennas to provide the receiver with a multiple uncorrelated replicas of the same signal. The information or the set of symbols what we are going to transmit would remain the same. Okay. So we have certain advantages, right? The complexity of having multiple antennas which is placed on the transmitter. So every transmitter needs to have multiple set of antennas which is naturally shared among the receivers and the forward base to mobile link in many wireless systems. So you have a basic system, a base transceiver station or the transmitter having multiple number of antennas. So transmit diversity is more desirable in systems where more space, power and processing capability is available on the transmitter side than on the receiver side, as best exemplified by cellular systems. Like our mobile phones, it is very difficult to have multiple antennas in your handsets. But it is quite possible to have an array of antennas from the transceiver or the base station side. Transmit diversity design depends upon whether or not the complex channel gain is known to the transmitter or not. Now let us consider two cases. To understand transmit diversity, we will be considering two cases. One is without the channel knowledge or what you call it as channel side or channel state information. Okay. This is called as channel state information or channel side information, CSI. So we'll have two conditions. The first condition we'll consider the channel side information is known at the transmitter's end The second one is that the channel side information is unknown at the transmitter end. That means that you are transmitting a set of information or signals from the transmitter to the receiver. The transmitter is, first case, is aware of what is being transmitted, the path gain, the channel information. The path gain is being known to the transmitter, first point. Second condition is that we do not have any information about the path gain. So we'll see both the conditions in which we find out what is going to, how, what are the different parameters like the average probability of error and outage probability in all cases, like we have found out for the maximal ratio combining or selection combining. Is that okay? Now, the second part what you are going to study, the channel unknown to the transmitter, is a unique scheme. It is known as the Alamouti scheme. That means that in the first scheme, you have a transmitter here, Tx, and you have a receiver here. Okay, there is a feedback system that is being fed back to the transmitter so that the channel information is known to the transmitter. So this is called as the first method. We'll find out the parameters for the first method. So the first case where the channel information is known to the transmitter. Let us consider a diversity system with M transmit antennas and one receive antenna. In the first case, let us consider M transmit antennas and one receiver antenna. The CSI, channel side information, that is Ri e raised to j theta I, the path gain associated with the ith antenna, is known to the transmitter. So let us denote the transmitted signal by S of t and let the total energy be Es. So like what we have done now, we are going to multiply with complex gain alpha I, which is equal to Ai e raised to minus j theta I, where Ai will be having the values between 0 to 1. Let this be the information that is being transmitted through the ith antenna, because we know the path gain, right? Yes or no? So like what is happening in maximal ratio combining, we'll have a complex multiplication where we'll be doing what is called as co-phasing. Okay. So now what we are going to do is that we are going to find the combiner output gamma sigma. So in transmit diversity, we are dividing the energy symbol into equal number of transmitters. Okay. And we have a weighted output at each transmitter. Then in that case, the received signal R of t is denoted by sigma I is equal to 1 to m Ai Ri St. Okay. We are weighting each signal. That means we are giving importance to the thing with higher SNR. Okay, the maximum value of Ai, that is the summation of all these things, will be 1. So now, like what we have done for MRC, maximal ratio combining, what we have to do is that we have to find the value of Ai. so that we get maximum the combiner signal to noise ratio, that is denoted by gamma sigma. For that, like what we have done in the previous, we can do two. One is by Cauchy-Squash inequality or by partial differentiation. And using that method, if we solve for AI, we'll get the value of AI to be Ri by root of 1 sigma I is equal to 1 to m Ri square. On substituting this value here, you will get the output signal to noise ratio to be, the combiner output to be equal to Es by N naught sigma I is equal to 1 to m Ri square. This is nothing but sigma I is equal to 1 to m gamma I, which is the instantaneous SNR at each branch. So we got the value of signal to noise ratio. The received signal to noise ratio is the sum of SNRs on each of these individual branches. So in transmit diversity, we have multiple transmit antennas and we are transmitting this through different wireless channels. Okay. We are considering two cases. The first case where the wireless channel path gain is known to the transmitter. The second case where there is no knowledge about the wireless channel to the transmitter. The first case we have found out the combiner output, the output of the all the transmit antennas together. We have weighted each of these and the transmit antenna gain or the transmit antenna with the channel information known to the transmitter is very similar to maximal ratio combining, which we have seen in the last class. Okay. The next definition what we need to know is the average probability of error. The probability of error, PS, standard definition. PS is equal to integral 0 to infinity PS gamma P gamma sigma of gamma D gamma. Okay. This is standard definition. I'll just write it down a bit more clearly. It will be equal to integral 0 to infinity PS of gamma P gamma sigma of gamma D gamma. The standard probability of symbol error. Okay. Now substituting the values and using what is called as Chernoff bound, like what we have done in our maximal ratio combining, we'll get the value of PS to be alpha m q beta m gamma sigma. We know that alpha m and beta m are constants, and beta m would be a constant that relates to the distance to average symbol energy. We have studied what is alpha m and beta m in our previous sessions. Okay, on substitution you will get what is the average probability of error. Now integrating this over this chi-square and distribution for the combiner output gamma sigma yields the average probability of error PS bar or PS tilde, which is less than or equal to alpha m into product of 1 to m 1 by 1 plus beta m gamma I, the average instantaneous SNRs by 2. This is the way. Now there might be questions like derive the average probability of error when the channel information is known to the transmitter for a transmit diversity system. So in that case, in the limit of high SNR, assuming that the average instantaneous SNRs are identically distributed, we get that gamma I average is equal to a gamma, and from that we'll have this average probability of error is approximately equal to alpha m beta m gamma by average gamma by 2 raised to minus m. So at high SNR, what happens? The diversity order of this transmit diversity is m. So both transmit and receive diversity is using the same as maximal ratio combining achieve full diversity order. That means you get the maximum. Okay. What we understand from this is that both, whether it is selection combining or any other method, the transmitter channel knowledge is same as under the receiver diversity. So in the first case, when the channel information is known to the transmitter, it means that it is almost same as maximal ratio combining, because you are capturing the path gain, you are feeding it back and working. Is that clear? So there is no much confusion here. We will be having more confusion in the next case where we do not have any path gain information about the wireless channel information to the transmitter. Okay. The second case, which is extremely important and more likely to appear in your question papers, is the channel is unknown to the transmitter. The transmitter diversity gain can be obtained even in the absence of channel information. This was done with a severe research work, and it was done by Alamouti. That is why it is called as Alamouti scheme. In this case, we do not have this channel side information at the transmitter. That is, we do not know what is Ri e raised to j theta I, the path gain associated with the ith antenna. So let us consider a MISO system. See, one more thing is that now we have an advantage of using transmit antenna because it is much more easier to have more number of transmitter antennas than the receiver antennas. Am I right? It is more easy to have large number of antennas in a tower than to have more number of antennas in your mobile set. So the obvious advantage is that in most cases, in most cases where there is a complex system, we prefer to have transmit antennas. You can keep this point in your mind. Now we are considering a MISO system. For the sake of our study, we will be considering a system where we will be having multiple input antennas and a single output antenna. Here, in our study for this particular aspect, we will be considering only two transmit antennas. And we are not bothered much about the receive antennas. We will consider it to be only one. Okay. We do not have the information of the channel, wireless channel in the transmitter's end. So let us consider ES to be the energy. Okay. So and if 2 is the diversity order, this energy is divided among the each time symbol. So we get it as ES by 2 for each transmit antenna. Okay. So we have two antennas. We are equally dividing this transmit energy between these two antennas. So if ES is the energy per symbol, let the transmit antenna on antenna I, let it be, see I is equal to either 1 or 2, that's it, right? S of 1 and S of 2, we are considering only two cases. And so we have a transmitter here, you have one antenna, you have another antenna, it is passing through this one, let it be H1, this is going to be H2, and this is being received at the receiver. So let the path channel gain, let us denote it by H1 and H2, and let it be Ri e raised to j theta I. We are not sure about what it is. Okay. We do not know what is it. Have you noted down? Are you able to understand? So we have denoted this by Hi to be Ri e raised to j theta I. Now let us consider a Gaussian channel with mean 0 and variance 1. In that case, the received signal R of t is given by R of t is equal to root of 0.5 H1 plus H2 S of t. So we have the receiver or the received signal to be R of t, that is equal to root of 0.5, because we are dividing the energy into two equal halves, right? H1 plus H2 S of t. S of t be the input signal. So I am going to explain to you a very important scheme called as Alamouti scheme. Let us consider we are sending two symbols S1 and S2 either at two different times through two different antenna 1 and antenna 2. Okay. In antenna 1, I am sending the signal S1 in the first instance and the conjugate of the second symbol, that is in antenna 2 I am sending S2 again. Now in antenna 1 at a particular time diversity or after a particular time I am sending the conjugate of S2 minus S2 through antenna 1 and the conjugate of S1 through antenna 2. Let us consider a system where we have two antennas, two transmit antennas. In this Alamouti scheme, I am sending two symbols, one S1 and the other S2 through antenna 1 and antenna 2 in the first time period. After that, after a period of time, I am sending the next two signals, that is the conjugate, the minus conjugate of S2 and conjugate of S1. Okay. Now let me assume that it is giving me two different outputs, Y1 and Y2. So let us assume that it is giving two outputs, Y1 and Y2. So the received signals Y1 and Y2 will be given by Y1 is equal to H1 S1 plus H2 S2. H1 is the channel gain for the first antenna, H2 is the channel gain for the second antenna, plus the noise N1 and N2. The vector Y dash, we define it as, we are going to convert this into matrix for solving this very easily. Okay, so let us consider a vector Y which is received at the receiver, and we are defining this Y to be the transpose of Y1, Y2, that is nothing but Y1, Y2 conjugate. In the previous communication engineering lab, we have learned that how to process matrix vectors. So in that case, we'll convert this into matrix equations by vector Y is equal to H1 H2 H2 conjugate minus H1 conjugate into S1 S2 plus N1 conjugate of N2. Again, for our convenience, we are indicating this by HA into S plus N, where HA is given to be this matrix, S this one and N this one. So now let us define a new vector called as Z, which is the Hermitian matrix of HA and Y. In that case, HAH, that is the Hermitian matrix, a complex square matrix that is equal to its own conjugate transpose. I believe that you would have studied what is a Hermitian matrix in your mathematics. It is nothing but a complex square matrix that is equal to its own conjugate transpose. Okay. So HA of H is nothing but its own complex conjugate transpose into H, that will be giving us the value of H1 square, the modulus of H1 square plus H2 square into I2. So in that case, Z vector will be equal to Z1 Z2 matrix. So substitute these values here. Z is nothing but H1 square plus H2 square into I2 into S plus the noise value. So now we are dividing N tilde, which is nothing but HA of H into N to the complex Gaussian noise vector with zero means and covariance matrix defined as E N conjugate, N tilde N conjugate, that is equal to nothing but H1 square plus H2 square into N naught into I2. So The diagonal nature of Z effectively decouples the two symbol transmissions so that the component Z1 corresponds to one of the transmitted symbols. So Zi is equal to H1 square plus H2 square Si plus the noise. The value of I is either 1 or 2. Okay. We have two values, right? So we are calculating or we are finding out what is Zi. The final one, what is the received SNR in Alamouti scheme? The received SNR gamma I is given by gamma I is equal to gamma I is equal to H1 square plus H2 square into ES by 2 into N naught. I forgot to mention here that N naught is the power spectral density. N naught by 2 is the power spectral density. And this factor value of 2 is given because we consider two antennas only, transmit antennas only, so that the energy is divided by 2. So we get this as ES by 2 here. So in case of M, we get ES by M. So significance of Alamouti scheme, the received SNR is thus equal to the sum of SNRs on each branch divided by 2. That means that we do not have the channel information, but still the received SNR is less. Am I right? Yes or no? The Alamouti scheme achieves a diversity order of 2, the maximum possible for 2 antenna transmit system, despite the fact that the channel knowledge is not available at the transmitter. So with these 2 points, that is channel information known to the transmitter and channel information unknown to the transmitter, we are completing what is called as transmit diversity. Okay, so in the first case, you will be asked to derive the signal to noise ratio, combiner output SNR, gamma, sigma, and the outage probability. Okay. The second case is the Alamouti scheme, where you are sending S1 and S2 two symbols in the first transit period, and then you are sending the negative conjugate of S2 in the first antenna and S1 conjugate in the second antenna. Okay, we are getting the output, we are processing that, and we are finding out the signal to noise ratio. Is that clear? Thank you all, thank you very much.